Arriba. ¿Así? Arriba. Bueno, pues comenzamos la segunda parte de la sesión, que ya nos vamos a ir centrando en el proyecto LIFE. Hemos estado hablando de contaminación de suelos, de agua, diferentes casos de descontaminación de estas matrices, modelización. Y ahora, pues, Jofra de Beca, que es nuestro centro coordinador del proyecto MySOIL, nos hace una presentación del proyecto.
Muchas gracias, Carlos. Como ha dicho Carlos, yo soy Jofra, vengo del Centro Tecnológico Eurecar y haré una pequeña presentación, simplemente introducción del proyecto para que luego mis compañeros y otras partes del proyecto puedan ir directo a los resultados y a los sitios que os quiero mostrar. Y al final de mi pequeña presentación sí que introduciré Eurecar como centro tecnológico del proyecto. Entonces, vale. El proyecto MySOIL se focaliza en suelos contaminados, principalmente de hidrocarburos. Entonces, ¿cuál es la problemática a nivel europeo? Tenemos alrededor de 2,5 millones de sites potencialmente contaminados. De estos, como mínimo el 14% requieren la descontaminación y de todos los tipos de contaminación tenemos alrededor del 35% son compuestos derivados del petróleo, ya sea por aceite mineral o también hay los BETEX y otros compuestos que entrarían dentro de la misma familia. Y como seguramente sabréis, como todos los compuestos de hidrocarburos de petróleo son muy diferentes y una de las características que nos quería aquí resaltar sería su degradabilidad. Como sabéis, estamos hablando de bioremediación, no todos los compuestos son igual de biodegradables y tenemos desde los alquenos, que son los más sencillos de biodegradar, hasta los más complejos, que son los asfaltenos y resinas. Entonces, ¿cuál es el punto de partida? ¿Qué se está haciendo a día de hoy o en el caso del MySOIL justo cuando empezamos? Tenemos que alrededor del 30%, este porcentaje varía un poco, depende del país europeo, en los suelos contaminados con hidrocarburos se gestiona a vertedero. Luego tenemos tecnologías físico-químicas, por ejemplo la disorción térmica o incineración, pero también pudimos encontrar otras como oxidaciones químicas, que tienen un costo energético y es caro, pero por otra parte son muy eficientes de eliminar todo tipo de hidrocarburos, incluyendo los de cadena larga, que son aquellos que son más recalcitrantes o poco biodegradables. Y por otra parte tenemos la bioremediación convencional, otramente dicho biopila con bacterias, que a nivel energético y a nivel de coste económico es eficiente, pero por otra parte siempre hay una parte de los hidrocarburos que no son capaces de degradar las bacterias. Y nuestra propuesta, o lo que queremos demostrar, es que la micoremediación, entendida como remediación utilizando hongos, que son los que nos ha contado antes Carlos, principalmente los lignocelulósicos, pueden o consiguen eliminar los hidrocarburos de la cadena, manteniendo los beneficios de la bioremediación. Vale. Después de esta pequeña introducción, este es el consorcio dentro del proyecto LIFE. Estamos Eureka como coordinadores. Tenemos 3 sites, uno situado aquí en España, que es lo que vamos a visitar hoy, que está coordinado por la Universidad Autónoma de Madrid y Kepler. Tenemos otro site a Italia, donde participan la Universidad de la Tuscia y Eni Reguay, y otro site localizado en Francia, donde participan principalmente Novobiom y Valve. Y para terminar el consorcio, que somos 8 partners, tenemos ISODT, que es una empresa alemana que nos da apoyo a nivel analítico, tanto a nivel analítico químico como biológico. Yendo un poco más a lo que es el proyecto MySOIL en sí, el principal objetivo es demostrar la viabilidad de la tecnología de micoremediación a escala piloto para eliminar hidrocarburos y manteniendo las condiciones de coste efectivo, vale, me está saliendo en inglés aquí, que sea adecuada, que sea eficiente y que sea sostenible, tanto a nivel ambiental como económico. Entonces, estoy viendo que el mapa no se visualiza muy bien. Vemos aquí, tenemos en Huelva el site español, en Rouen, lo he dicho en español, no pasa nada. Tenemos el site francés y en el caso italiano utilizaron 2 emplazamientos diferentes. Primero trabajaron uno en Borgo Fatti y otro, tenemos el piloto ahora en Siciliano. Y el proceso, las etapas que hemos trabajado a lo largo del proyecto es empezar con una caracterización del emplazamiento, luego unos test de viabilidad de este suelo con el tipo de hongo y el sustrato, que son experimentos en microcosmos de 1,5 litros. Luego, y ya hemos hecho unos pilotos pequeños de un volumen de 1 metro cúbico, los hemos llamado mesocosmos, que ha servido para hacer el escalado de esta tecnología, y finalmente los pilotos en sí, que son pilas, biopilas o mycopiles si tienen hongo, de 50 metros cúbicos, que es lo que veremos hoy. Siendo adelante, ¿cómo evaluamos si la micoremediación es eficiente o no? Aquí os haré unas pinceladas de qué parámetros estamos evaluando, pero luego los compañeros de los 3 pilotos os darán un punto de vista mucho más concreto del que han hecho ellos. Tenemos estos 3 pilotos actualmente. De hecho, actualmente el de Rouen ya ha terminado, el de Siciliano está a medio camino y el de Huelva pues lleva un mes, creo, justito un mes. Entonces, por una parte es obviamente que tenemos que evaluar parámetros convencionales, ya sea temperatura, nutrientes, los gases y obviamente también la eliminación de los hidrocarburos del petróleo. Pero también hemos querido ir un poco más allá. Hablamos de los indicadores de salud del suelo, como ya han dicho, creo en la segunda charla, tenemos esta nueva ley europea y se está desarrollando un marco normativo importante que no solo evalúa la eliminación del contaminante, sino otros indicadores para ver cómo quedará el suelo. Y también estamos aplicando una serie de herramientas de monitorización avanzada, ya sea a base de isótopos, a base de los ácidos grasos, o desarrollando una herramienta, un device, un equipo, para poder evaluarlo in situ. Esto os lo contará el siguiente ponente de ISODT. Y asimismo, cuando queremos evaluar si una tecnología es buena o no, tenemos que hacer una integración de diferentes evidencias. Y luego hacemos una evaluación del ciclo de vida, un impacto socioeconómico, un una evaluación del ciclo de los costes económicos y también una evaluación del riesgo a la salud humana. Como lo han dicho antes, creo que ha sido sobre todo Cintia, pero también un compañero más, el análisis de riesgo de dónde partimos y hacia dónde llegamos, que es muy importante porque el límite o el objetivo de concentración nos lo marcará esta evaluación. Entrando un poco más en indicadores de salud del suelo, aquí solo he puesto una diapositiva, creo que ya se ha hablado un poco y no sé mucho bien el nombre de la directiva esta. Básicamente nos define un tipo de indicadores que a día de hoy hay varios proyectos que los están estudiando, cuáles son estos indicadores, cómo se tienen que evaluar, tanto físicos como químicos como biológicos, y el foco principal es llegar a las funciones ecosistémicas del suelo, que es para qué nos sirve este suelo. Y nuestra intención con la micromediación es, como mínimo, mantener o mejorar los indicadores o características físicas y químicas, mejorar los indicadores biológicos y restaurar las funciones ecosistémicas de ese suelo. Ya cerrando mi pequeña presentación sobre el proyecto MySOIL, entramos que aparte de estos 3 pilotos, estamos desarrollando, y al final del proyecto las tendremos, unas guías de implementación de la microremediación, para que lo que se haya aprendido dentro de este proyecto haya también una mejora y una distribución de conocimiento generado de este proyecto. Y estas guías, aparte de los 3 pilotos que tenemos, estamos haciendo experimentos de replicabilidad, que los estamos haciendo por una parte desde Eurecat con los sustratos exhauridos de hongo, o SMS en inglés, y también desde Nuevo Guión con inóculos fúngicos que tienen ellos en su librería. Y yendo un poco más allá, también, que creo que ha ido bien que ya habéis presentado, creo que ha sido justo, esta charla sobre los HTF, sobre los aceites de las placas solares. Haremos unos experimentos o unos ensayos de transferabilidad, que si la aplicación de esta microremediación en hidrocarburos también se puede utilizar para este tipo de contaminación. Estamos ya en fase de empezar el piloto en breve. Finalmente, también haremos unas contribuciones a los estándares y regulaciones europeas que hemos encontrado a nivel de normativa que aplique a nivel regional, estatal o a nivel europeo. Por eso también ha sido un poco interesante la segunda charla. ¿Cuál es la salida de un suelo descontaminado? ¿Qué se puede hacer con él? Al momento que sale del emplazamiento y es un residuo. ¿Hay mercado para un suelo descontaminado fuera del emplazamiento para reutilizarlo? Realmente no hay, pero es problema de la normativa, es directiva, que no se está buscando un valor de ese suelo descontaminado. ¿Qué se puede hacer? Y esto, aquí hay una gran diversidad a nivel europeo. Cada región y cada país tiene una predisposición diferente a utilizar estos suelos descontaminados. Estamos trabajando en este white paper que tratará estos temas de implementación y a nivel normativo, no solo microremediación, sino de la bioremediación y de las problemáticas de in situ, me queda poco tiempo. Vale. Y hemos hecho varias actividades de inspiración. Si no nos seguís en las redes, por favor, hacedlo. Principalmente utilizamos el LinkedIn y la página web, pero también estamos activos en Twitter. Finalmente, como tengo poco tiempo, lo haré en 1 minuto máximo 2. Eurecat. Eurecat es un centro tecnológico, nace hace 6 años de la unión de diferentes centros tecnológicos en Cataluña. Nuestro foco es, a partir de experiencia y capacidades que tenemos, ayudar en diferentes ámbitos. Actualmente tenemos 11 sedes en Cataluña, pero han abierto un par nuevas en España, en Madrid y en Málaga, y tenemos otra sede también en Chile. ¿Qué más? Nuestro foco es llenar el vacío o el posible vacío entre lo que es académico y universidad y lo que necesitan las empresas. Y es básicamente este desarrollo de investigación aplicada. Obviamente tenemos que trabajar con universidades y otros centros de investigación más puros y con las empresas que estén dispuestas a invertir en I+D. Dentro de Eurecat, varios ámbitos, diferentes líneas. Aquí veis la parte industrial, digital, biotecnología y sostenibilidad. Participamos principalmente en la línea de suelos y aguas subterráneas, que tenemos diferentes focos, desde la modelización a la monitorización y análisis de riesgo de suelos y aguas subterráneas y aplicación de estrategias de remediación en aguas subterráneas y suelos. Este es el equipo que hemos participado, o estamos participando en este proyecto MySOIL, y creo que muchas gracias y podemos... Ya, pero... Sí, así, ya.
Hello, can you hear me?
Yes, we can. You?
Yeah, fine. Thank you.
Okay. Okay, we can. I am going to do a short presentation and we start, okay?
Hello?
Uncle, do you hear us?
I can hear. Should I start the presentation?
Yep. Yeah, we can start.
Okay.
Pues el siguiente ponente de la sesión es Anko Fischer, de la empresa ISODTEC, y bueno, nos va a hablar sobre unas herramientas que están desarrollando en la empresa para monitorizar mycoremediation. Anko, is your place.
Okay, thank you. Unfortunately, I can not be with you due to a strong infection, but however, it's nice to give the presentation also online. Yeah, my title is Advanced Monitoring Tools for Assessment of Natural Pollutant Biodegradation and Success Control of Bioremediation. First, shortly, I want to introduce ISODetect. We provide environmental monitoring tools, for example, stable and radioisotope analysis, also metabolite analysis, just to give some explanations. And we have three main fields of work, which are contaminated sites, where we do, for example, source apportionment or evaluation of pollutant degradation. Then the other working field is groundwater and drinking water resources, where we do groundwater age dating, or we investigate interactions of surface and groundwater. And finally, we have the working field, renewable and fossil energies. And there, just an example, we evaluate microbial processes in hydrogen underground storage or in biogas plants. But now I want to come to the main topic today. And I give you a brief introduction into the contamination at the site. Most of you know this. When a contamination occur, there the contaminant enter to the subsurface, first in the soil, then also in the water unsaturated zone, and finally it reached the aquifer, and there it spread with the groundwater and create a contaminant plume. There are several processes that lead to a decrease in pollutant concentration, which are mainly which are mainly sorption, volatilization, dispersion and dilution, and biodegradation. And these are also known as natural attenuation processes. But however, the physical process shown here in blue lead only to a spreading or displacement of pollutants and not to a reduction of the contaminant mass. Only the biodegradation is a sustainable reduction of pollutants, which means that also the pollutant mass is reduced. As I already explained, all of these processes lead to changes in pollutant concentration. Therefore, physical processes and biodegradation cannot be distinguished by just only pollutant concentration analysis. So therefore, other methods are required. There are a toolbox of methods for evaluating pollutant degradation. Here I distinguish these in semi-quantitative, quantitative tools and qualitative tools. Semi-quantitative, quantitative tools are compound-specific stable isotope analysis, lab microcosm treatability studies, molecular genetic tools, for example, qPCR analysis, or in situ microcosms, for example, bug traps. And the qualitative ones are metabolite analysis of pollutants, GCMS fingerprinting, or GCMS screening. Here it means qualitative. This gives just an indication or proof of degradation, and semi-quantitative or quantitative, this gives also a kind of quantification of the pollutant biodegradation. Now I would just shortly give some brief explanation of these tools. What I mentioned as metabolite analysis is to detect the intermediate products of biodegradation. It gives clear evidence of biodegradation, but it's only quantitatively. It's mainly applied for pH, BTEX, MTBE, TBE, or also alkanes, and aerobic and anaerobic biodegradation can be distinguished. Then we have the GC fingerprinting, GCMS screening, which is also suitable for forensic source discrimination besides the assessment of degradation. It's mainly applied for complex contaminant mixtures, for example, petroleum hydrocarbons. In order to evaluate the biodegradation, it's take the advantage that some of the pollutant classes are more biodegradable than others, and this leads to changes in the pattern of the composition of the petroleum hydrocarbons, and therefore it can be, the biodegradation can be evaluated. That means there are more biodegradable and more persistent compounds, and this can you see in a change of the pattern of the composition of the petroleum hydrocarbons. Now the semi-quantitative tools or quantitative tools, there are the compound-specific stable isotope analysis. This is the measurement of stable isotope ratio, for example, for carbon or hydrogen of contaminants. Mainly you compare this isotope ratios from a source zone with this in a contaminant plume. And if you see significant changes in the stable isotope ratios, this gives proof of biodegradation of a specific pollutant, but also it can be applied for quantification. And it's mainly visible for smaller molecules of pollutants like chlorinated ethenes, BTEX, MTBE, TBE, chlorobenzenes, some pesticides, nitrate, methane, and so on. qPCR. With qPCR, you measure the abundance of specific taxonomic or functional genes, and this gives you information about the degradation potential. It's a semi-quantitative tool because the proportionality of to the real degradation activity is sometimes unclear. You have the amount of your taxonomic genes, but if this is directly linked to the real degradation is sometimes not clear. So you can compare the amount of your specific genes from different sampling points and can see if maybe the potential is higher in one of these sampling points. it can be applied for a lot of pollutants. Most prominent ones are chlorinated ethenes and BTEX. And then we have this bug traps. This is in situ microcosm where a certain C-labeled contaminant is absorbed, and then the certain C-label finally can be detected in biomolecules from colonizing microorganisms. It's a selective tool to prove mineralization of specific pollutants, but it's only feasible for metabolic biodegradation, not for co-metabolic biodegradation or reductive biodegradation. It's a semi-quantitative tool because you can compare the certain C incorporation in a biomolecule from which are extracted from the bug traps from different sampling points. And in the sampling point where you see the highest certain C enrichment, this is also the sampling point where you can expect the highest biodegradation. What are the criteria to select the monitoring tools? First of all, the tool should be suitable for the respective compartment, the soil, the groundwater sediment, or the water unsaturated zone. Sorry. Yeah, then the tool should be available and suitable for the target pollutants. And it should be also compatible with other monitoring tools. And of course, last but not least, it should be affordable financially and in terms of workload. And this criteria we took and evaluate what are the best monitoring tools for MySOIL. The initial situation is that we have as compartment soil, which is polluted by petroleum hydrocarbons, and we want to evaluate the biostimulation in bio and mycopiles. Based on this, we selected several methods besides the concentration analysis of the petroleum hydrocarbons. We selected the GCMS screening, the mycotraps, which is a novel in situ microcosm, and molecular genetic tools were selected, which are provided by other project partners than ISODetect. First, a brief information about the GCMS screening. You see here the procedure. You get the soil samples from the field site. The petroleum hydrocarbons are extracted by SOX extraction. Then the extract is injected in a GCMS system. And I would like to give just a short example of the results. What you can see on the upper part on the right, you see a total ion chromatogram. That means the main petroleum hydrocarbons are between C8 and C25 alkanes. So that means this is a middle distillate. And already there you can see normally in a fresh middle distillate, you see significantly more single peaks. Here you see a very pronounced hump of unresolved compounds, which means or which indicates already that the petroleum hydrocarbons have a high degree of weathering. Then on the left-hand side, you see the single ion chromatograms of specific compound classes, N-alkanes, alkylbenzenes, isoprenoids, and steranes, and also tri-aromatic steroids. And from the top to the bottom, you have a decreasing biodegradability. And normally the N-alkanes are most pronounced for petroleum hydrocarbons, for example, in diesel and heating oil, but here are only a few can be seen, and more pronounced are alkylbenzene and isoprenoids. And this gives again the indication that the petroleum hydrocarbons are already strongly biodegraded. And finally, in the table, you can see these are diagnostic ratios which are specific for evaluating biodegradation. And on the top, you have the a ratio of an N-alkane with the carbon number of 17 to pristine, which is the isoprenoid. And similar to this, you have on the lower button, you have an N-alkane with the C18 and the isoprenoid, the phytane. And you see the measured ratios are already lower than 0.2. And in fresh middle distillate, we have ratios between 1.5 and 2.5. And this gives finally the proof that we have here a middle distillate which is significantly biodegraded. So finally, for all the three pilot sites, we found aliphatic petroleum hydrocarbons has the highest priority, and they are subject to advanced biodegradation. Now I would switch to the other tool, which are the microtraps that we applied. Normally, you know, the petroleum hydrocarbons consists mainly of carbon and hydrogen. And for carbon, you have two stable isotopes, one with the mass 13 and one with 12C, or with the mass 12. And under natural isotope abundance, certain C has significantly lower abundance. It's approximately 1% to 99%. And what we apply here is 13 C labeled compounds, which means that we have then in our compounds certain C composition of 99% nearly. And this we can apply to the microorganisms, and when they convert this certain C labeled compound, you find the certain C label into mineralization products like CO2 or into the microbial biomass. So we established there a concept where we first load a certain C-labeled target pollutant to an in situ microcosm. This will be installed into the soil and for an exposure time of several weeks. After this, we remove this in situ microcosms and extract the biomarkers. And with the compound-specific stable isotope analysis, we can determine the certain C incorporation into the biomarkers, which will give then, when we see a significant certain C enrichment into the biomarkers, this gives direct and significant proof that the target pollutant is biodegraded within the soil or the soil experiment. And we have several, or we can select several biomarkers. We can choose fatty acid, or more specifically phospholipid fatty acids of the cell membrane, amino acids of proteins, or RNA and DNA. In our approach, we used phospholipid fatty acids because it can be, the effort is not so high to measure the certain C incorporation into the phospholipid fatty acids, and it gives also some taxonomic information. I will give you some results of a mesocosm test in Italy. We applied their mycotraps in stainless steel cartridge with soil from the field site, and we use certain C-labeled hexadecane as a target pollutant. And first of all, I want to show you the PFLA pattern, the phospholipid fatty acid pattern. On the top, you see this from the mesocosm, which were inoculated by fungi, and on the bottom, you see the control. And there are bacteria-specific phospholipid fatty acids. They are mentioned there. These are mainly fatty acids with a carbon number of 15, 16, and also 17. But there are also on the other side fungi-specific PLFAs with mostly carbon numbers of 18. And actually, what you can see between the inoculated and the control ones, the pattern are nearly similar. In the C18 range, you see in the inoculated mesocosm a little bit higher amount. So this is probably related to the addition of the fungi to this mesocosm. And now, next result shows the certain C enrichment of the phospholipid fatty acids. Just to explain how to express the certain C enrichment, we measure the so-called delta certain C value, which is a ratio of certain C to 12 C from a probe or sample compared to an international standard. We do this because this delta certain C values can then compared worldwide. And normally you have the natural isotope ratio, carbon isotope ratio, the delta certain C values of phospholipid acids on the negative range. They range between -35 and 10 delta per mil. And on the scale, you can already see that we start here with 0 delta per mil and up to 2,200 delta per mil. This shows that there is a significant certain C enrichment into the fatty acids. Surprisingly, the certain C enrichment were higher in the control than in the inoculated. Once the inoculated are shown in red, the control shown here with the bars in blue. But however, we had a successful proof of complete mineralization of certain C hexadecane and successful validation of the microtrap concept. And this we tried also for hydrogen isotope labeled compounds. This means we can use the deuterium labeled. Deuterium means the heavy hydrogen isotope labeled. We can use compounds. Why we do this? They are less expensive and more available. So you see there the natural abundance, which is very low for the hydrogen with the mass 2, or it's also known as deuterium. And in deuterium labeled compounds, you will have an labeling of the deuterium up to 99%. And similar like for the certain C labeling, when the deuterium labeled compound is biodegraded, you will see a deuterium enrichment in water and in biomass. We tried this. We see here results of the mesocosm experiment in Spain. On the upper part, you see a phospholipid fatty acid standard. And the brownish or the brown line shows you the mass trace of the hydrogen with the mass 1, and the green line shows you the hydrogen with the mass 2, which means the deuterium. And when you compare the upper chromatogram with the lower chromatogram, you see that in the lower chromatogram from the mesocosm experiment in Spain is very strongly increase in the green line, which means there is a very strong increase in the deuterium amount. So this is even above that we can measure delta values for hydrogen. This has such a strong enrichment that we cannot data mine this with the enrichment. However, we see a strong deuterium enrichment in phospholipid fatty acids. It proves the mineralization biodegradation of the deuterium labeled hexadecane. And we have the potential there for cheaper microtraps because the deuterium labeled compounds are available for more target pollutants and they are also less expensive. So coming to conclusions and outlook, throughout the evaluation of pollutant biodegradation requires appropriate monitoring tools beside the concentration analysis. The suitability of the methods must be determined according to the availability of the target pollutants, the site conditions, and the financial possibilities. Beside the microtraps with certain C-labeled target compounds, there's a potential for microtraps with deuterium-labeled target pollutants as cheaper option and for a higher variety of compounds. The next steps are the microtrap tests in the mycopile experiments in France and Italy. They are already finished and now we investigate. They are under investigation. We do the analysis. On the one hand side, the GCM is screening, and on the other side, we do the analysis of the certain C enrichment and the deuterium enrichment into the phospholipid fatty acids. In Spain, the microtraps will be installed soon. Thanks for your attention.
Thanks, Anko. Bueno, aprovechando mientras cargan la siguiente presentación, vamos a ir ahora presentando los diferentes ensayos que hemos hecho en los 4 sitios. Vamos a empezar con el sitio francés, con las biopilas que se han realizado en Seville. Y lo va a presentar Lauren Tannenberg de Valgo y Jean-Michel Neure. Sorry. Jean-Michel. De Novio, empresa belga, que han estado trabajando en conjunto. The technical team. Sí. I know you like to. Sure, you like to.
Yeah. Good morning, everybody. As Geoffrey told you, we have 3 sites in the MySOIL project, and we will present together with a binôme in the consortium of the partners, French and Belgian consortium to the what we call the French site. I will present you the site. Just rapid overview of Valgo involved in this project. So I didn't check the quality of the slides from the projector on my computer. It was okay. So Valgo proposed remediation of sites from the brownfield to the installation of new activities with demolition, asbestos removal, remediation of soils, and projects. So we have a whole chain of renewing the terrain and the industry of science. I'm the research director of the company, and so I'm involved in seeking new possibilities of the remediation of the pollution. I will briefly present the site. We are in the northern part of France, in the region of Normandy, and you see in this curve of the Seine River, this is just south from the city of Rouen that is here, and this is a very big industrial part, just close to the Rouen harbor. And there is a refinery in this site that we bought in 2014. It was a former Shell and Petroplus refinery. It was of, I don't know, no. Pass. Oh, yeah. Okay. So this is the storage part was sold at the beginning of the works, and we concentrate on the 90 hectares part of raffinage plant, and we dismantle this and remediate the soil. And today, most of the virtual building on the picture are now really welcoming new industrial activities and different companies. Half built to date, and we achieved this huge work. And this is in this area that we determine different spots of pollution that was good candidate for the MySOIL project, and one under what we call a river of pipe in the middle of the refinery, one of the spots. It was big here, and we collected all the soil for the different steps of the project. This is what we use for the medium-sized experiment. We sent some in Belgium to make the selection of fungal strains, and what we will present in bigger pies in the second part.
Thank you. So, disculpe, no voy a seguir en español, voy a seguir en inglés, pero pienso que está mejor. So, first of all, thank you for Kevin for organizing this very interesting day. I've been busy presentations before, so it's very, very nice to be here and to have a chance to interact. A few words on, so I'm Jean-Michel, and the co-founder of La Rábida, with Caroline Zavida. And before going to the project, I'll just say a few words about what we do. We specialized into leveraging the potential of biotechnology for environmental applications, with a specific focus on using fungi in different domains. One is the bioremediation sector, but also we're working on waste recycling and basically. And is it that? And I'm not going to spend too much time on this because it has been well covered this morning through a different presentation about the complexity of bioremediation, but also its potential, and the importance that what we call now precision bioremediation is using advanced tools that are coming from the life science, like metagenomics, DNA analysis, data points, actually to help driving and optimizing bioremediation potential to target more complex pollution, but also to better understand what's happening within the bioremediation plan. And this is what we call more the precision bioremediation. That's also coming from precision fermentation, precision, where these tools are already used quite commonly in life science or in other sectors of bioremediation. So, and into that, what do we do? And we combine different elements. And one key aspect, we'll spend a bit of time on that because I think it's very complementary to what has been mentioned earlier this morning. We're currently building what we call a digital twin, digital platform, where we go back into how does the biology works, identifying the metabolic pathways. Why is a fungi capable of eating contamination? What is in his genome actually? Why, based on his genomic structure, how the organism works? How can we simulate that? And we're building the biological model of that, enabling us to simulate in silico environment the conditions, the reasons, what is missing, and not just focusing on the fungi. So by the end of the year, we'll be able then to simulate the interaction between the different microorganisms in the soil system. And this is very important because we try to bring some additional knowledge, and we have a very interesting presentation about the potential of bioremediation, but also the potential of modelization. And there, where we saw the models, where we're focusing on indeed the physical-chemical informations, and this is where we focus on biological information and how we can leverage it. But this alone is not very useful. And that's why we also have the second breakout. What we do is working in trying to select, isolate specific strains. We have over 300 now, and we have selected, isolated very extreme environments, highly contaminated sites, in waste streams, then we qualify. And then the last bit of that, if we want to make use of that, is the capacity to produce these inoculums in the right form for a given application. And that's where we're going to discover a little more into the project. We're focusing on different fermentation technologies using waste as a primary resources. Depending on the type of strains that we use, the production setups will be different. And this is for us the combination that enables us to this kind of platform to leverage the potential towards biotechnology in different sectors. So that was for number one. That was nice, but the project has been done before we're building them. So we're currently building all these tools, although we use the results of the project to nurture the modelization. But we don't have, I will not be able to show you today the results of the modelization and the choices that we made in the past are based on more traditional. And as mentioned by Geoffrey early on, so the first step into the process was to identify which is the potential fungal candidate, the most interesting one, targeting more heavy long chain hydrocarbons. And therefore, we did the Mailcom test. We screened over 71 different strains. We identified the right conditions because a strain doesn't work alone. It's working within the soil environment, but also with the right working on the structure of the soil to give it the potential towards driving the bioremediation. That was the first phase. We came out with three soil strains that were of interest, plus 3 different structuring components and 500 strains that we tested. And we had the first concentration was 5,000 milligrams per kilo, and we reached down to 82% of the population. Then came the second phase of the mesocosm. We're working on the cubic meter level, where we tested also different approaches. And there we start settling. We start settling on saying, okay, we can work on biostimulation, but thinking about, okay, how we can leverage the potential of already present mushrooms within the soil so towards biostimulating, more directed towards the fungal communities there, or adding a specific fungal strains from the experiments. And there we tested these two conditions into different setups, into static, dynamic, biopiles, and different elements. We had some, you saw the pictures, you saw that one. Some takeaways from there is that you realize that we probably had some problems with the content of organic matter because we use quite a lot of bulk agents, different ones, and then we have to reanalyze the data, and we decided to re-perform some microanalysis at a small scale before preparing for the data. And then comes now the last scale demonstrator we're going to present now, and I give back you to explaining a bit the different steps, and especially the first phase of the sampling strategy that has been.
Yeah, thank you, Michel. That's
well, just
sorry. That's
still yours. Asking me.
Sorry, you come slide.
And that was an example because there were 2 elements within the demonstrator that we did. So one focus was also to scale up the production of a given fungal strain that is adapted to a different scheme in a cost-competitive way. And this is the demonstrator where we upscale that in traditional techniques that are already available. And also very scalable at a very low price in terms of production. But that is a new case where we used a non-traditionally produced fungal strain that we fermented on the waste stream in a conventional fermentation framework that has been validated also.
Yeah, this is just between the 2 activities, because as I told you, present use stored soil during all the mesocosm phases. This amount of soil was stored under membrane to be protected. When we in June 23 or July 23, we started the mixing of the just presented inoculum that was produced by Neurobiome, and building one biopile with only biostimulation and one mycopile with bioaugmentation, fungal bioaugmentation. So we build the pile, cover them, install the ventilation system, and some samplers also point, and also the microtraps from isodetect you just seen before. And this is the starting point of the last step, the 6 months experimentation in larger scale. We improved a new way to make the sampling. It's just a manual probe, and when you make the hole, it's very easy to push the tube to prevent collapsing, because with the amount of organic matter, the soil is not very strong. It has a property potential to collapse in the hole. So this is a good way to just discard the 21st centimeters, and you are able to collect 80 centimeters beef to mix them before to send it to analysis. So this is the way we did this, and you see there are different zones where are some humidity and conductivity, or humidity and temperature probes, and also the zone of collection. The numbers are figuring the microtraps on isodetect, and we have a pattern of sampling each month in one direction around to recover each time where we have collected the months before. So we have a collection of physical information there and more chemical evolution on the right. And you see that's what happens. This is a real aggregate of soil we obtained with the mixing with the mechanical shovel. This is about around 10 centimeters, and you see that there are spots of hydrocarbons. And if you use alu mixer, as I have seen on the Hosto presentation this morning, you may cut it in 1 to 5 centimeters. It's a bit smaller, but you will still have some particles. And when you make some micro sampling when you send the sample to the lab, you may add one or not of this black part, and this gives a huge heterogeneity. So for the last months, we try to understand this way of where is coming the heterogeneity. You've seen that we have 5 points of sampling around the pile, and to understand if it's okay, one face is facing the sun, one is exposed to the wind or to the rain. We have to understand the heterogeneity between the points. So in each of the hole, I took the 80 centimeters I told you, mix them, and make 3 replicates for the analysis to understand the internal heterogeneity of the samples and the external, the inter-sample heterogeneity. There are some group of 3, the 3 repetition of the different sampling. And in the left, there are the mycopile sampling. On the right, more blue, there's the biopile sampling. So you see that all results are different. There is no one zone of sampling that is quite different. If I just analyze the variation values, we have some. This is the average variation for mycopiles. This is the average variation for mycopile, and the internal variation for each of the sample. You see that's very variable, and this is the point that you have to integrate, understand when you have a small degradation, maybe the variation is bigger than that. And this is a very important point to understand what happens, and not hurry to make conclusion when you observe small variation, because it's very that's the reality of the replication in soil. I also try to check on this sampling of the last month if there is a different of pattern. Maybe in some zone, light compounds could be faster degraded, even if I don't see the information on the average value of hydrocarbons. Maybe there is a split or an offset in the pattern of the different size of the hydrocarbons, but you have the mycopile on the upper line and the biopile on the underline, and you see that there is no strong difference, maybe a bit more of the gray zone in the biopiles and in the mycopile, but there is no heavy trend in condensing one in another one in this heterogeneity. So this is not the only explanation. I think that's yours.
Me again.
Yeah.
So in terms of results, so but the first thing is that maybe we should ahead. So here you can see what we call the bioimitation of mycopile. So that's where we did a specific inoculation of a specific strain. And the other one is the biostimulation, where it was with a specific structuration of the soil, but where the structuration agent has been conceived in order to mimic and to stimulate more in favor normally the fungal community. So it's not just compost, it has been a specific, we were looking at the carbon nitrogen ratios in terms to play with the carbon nitrogen ratios within the soil in order to drive some more fungal based degradation. What we see here, it is indeed at the beginning, we have the first 3 months before implementing a different sampling strategy. We had quite a higher heterogeneity levels in the measurements, which also drive a more complex interpretation of the results. But what we can see, what we witness is two different dynamics within the two systems. In the first system, you had quite a high degradation rate into the medium and the small part hydrocarbons in the beginning. That followed on with a later stage degradation of the longer ones, and quite a stable degradation over the time in terms of kinetics. Where into the biostimulated one, where we witness is that you have a quite low degradation at the beginning. You have a strong release of contamination in the second month, and then in the third month, the biodegradation started to be higher levels, especially in the framework that we did in the 6 months. We saw that degradation were more focusing into the biostimulation part, into smaller carbon chains, but not into the long ones. And so these are what is not primarily the results. We haven't finished analyzing all the results because there's all information that is still missing. I come back now. Is that we haven't done all the metagenomic analysis. So we're currently processing the metagenomic analysis to understand, okay, what is the evolution of the population? Do we see an increase into fungal population within the biostimulation? Well, how was that? How does the metagenomics help understanding the behavior within the two setups? And this is the data that we're currently processing. We're going to have information in the coming months too. And for us too, is that will enable us also to feed the modelization part, to understand the interaction between the fungal communities, the bacterial communities there, and to validate the modelization to them. So this is, and some interesting part is that to see, so here's the degradation rates that you have over the, after 6 months in terms of fraction. What's important to highlight is that you have in green, you have the mycopiles, the bioimitation ones, and in brown is more the biostimulated pipe, where you see that you have some differences. But the more different one, important one is here, where you see that within, when we tailor specifically, so a specific strains with a specific substrate within the soil, that is in terms of carbon nitrogen ratios, in terms of logic, in terms of what can happen in terms of metabolic process too, we see that we can achieve some degradation into the long chain. What is not the case with, we didn't achieve so far with the smaller, with the biostimulated one. So we don't have yet the whole answers into that why and what happened there, but that's something we're going to have in the future. But we see already a difference in terms of behavior based on the two configuration. So some takes away, some conclusion and outlooks and takeaways for a moment. one important point is that explained by Laurent is the sampling strategy to face the heterogeneity and being able to better have a fine understanding of when you have small variation on different elements. That's very important. The tailored bioaugmentation, I name that tailored because it has been a conclusion of a lot of tests, and we're probably going to have more hints in what's happening through the models soon, can lead to the degradation of the long chain, and also the fact that is one of the main objectives of the mycoremediation approach is to enable the degradation of the longer chains. We had some very different dynamics between the biostimulated one and the bioaugmentative approaches. But it's important also that some elements are missing in the understanding, and that's where in all the analysis that we're currently doing, understanding the metagenomics, we have a better steer, better take the knowledge and the knowledge around what's happening. One additional comment is that what we did now in other pilots and other tests is that we work with different types of strains. So here was the strains that was about Indica. It was a strain that was growing on wood waste. That's the principle. And now from the results that we have and from the screening and also the help of the modelization that we're using, we understand we have different strains, hard strains that do have the same potential in terms of degrading complex contaminants. And this one, we're probably going to have better proof. And with these strains, we achieved in similar context, we achieved very good degradation rates after 4 to 5 months in the same time. So the results are very interesting, but there are still some explanation work to be done, and we're probably going to have that. You want to add something to it? So thank you. Sure.
What is your procedure? I have to use glasses. I don't see. I don't know where it's located. Jorge, por favor, puedes venir. Vale, está bien. I did it. Any of the last one? Yes. Okay. Está cambiando en otra carpeta. I think the okay, good morning. First of all,
Alessandro. No, la próxima charla, vale, vamos a ver la presentación sobre el sitio italiano y correrá a cargo del profesor Alessandro Danibali de la Universidad de la Tustia. Fiora Bagnato de Energy Park no ha podido venir, está conectada también.
yes, and a few words very yes. Yeah, as it was told, this presentation was expected to be held jointly by the industrial partner, which is the Energy Wine company, and the academic one, which is University of Tuscia, that I'm representing today in this open day event. Unfortunately, due to last-minute inconveniences, the ENI officer was forced to give up to participate in this event. Thus, I have received the mandate to present also data that were designed and implemented by anyone. Okay. So, as our coordinator mentioned, in the early phases of the of this project, the whole consortium agreed to use an approach to mycoremediation, where the process scale was progressively increased, starting from biotreatability tests, which were mainly aimed to find the best combinations of bulking agents and fungal strains, to pass to the mesocon scale, where we tested a multivariate set, but at a consistent process scale of 1 cubic meter, to reach finally, at last, based on the relevant body of information acquired, to the implementation of full-scale biolines. So our project started from a soil which was collected in a petrol station located in Borgo Faidi in central Italy. Soil with a decidedly clay texture, a salt-alkaline soil with a hydrocarbon load in terms of C12, C40 of around 7,000 ppm, and where the most relevant fraction was done by C13, C18 hydrocarbons. So the biotreatability tests enable us to select 2 Pleurotus striatus strains and the bulking agent. In this case, we selected with straw, and led us to the decision also to recruit spent mushroom substrate as the inoculant in the mesocon scale. And this slide shows a graphical scheme and a real image of the plant, of the mesocon plant, which was installed outdoors in a site owned by Energy Wind, and which was made by 8 identical reactors in HDPE and IC stainless steel, built out with insulated cover and with a removable insulated cover. The ventilation was used as slotted pipe located in the bottom of the reactor, connected to a blower, and thus the air flew across the treatment bed from top to down, and the air coming from the blower was addressed to an activated carbon air treatment system before being released into the atmosphere. In addition to the strains, no, it's okay. So these images refer to the pre-loading operation where the soil was laid into an HDP liner, cobbles were removed, then the soil was pre-mixed with the bulking agent with straw. I remember to mention that the moisture content of the soil was adjusted to 70% of its fill capacity before its mixing to the bulking agent, and then this mixture was loaded into the reactor with the aid of a bucket excavator. Okay, this slide describes the experimental setup of the mesocon space, where we explored mainly 2 variables, namely the type of inoculant and the treatment bed configuration layout. In particular, with regard to the treatment bed layout, we explored 2 options. The former, a single layer configuration where the active inoculum was placed between 2 layers of soil, and a multiple layer, the second option, in the attempt of increasing contact surfaces between soil and the inoculant. And the second variable that we explored was the inoculant, and IF-type inocula refer to the strains that have been selected during the biotreatability tests. So they are arsenic cultures of 2 Pleurotus striatus industrial strains. The remaining mesocons relied on spent mushroom substrate as the inoculum, which was explored at two loads, namely 30 kilograms and 60 kilograms per mesocosm, and obviously in different treatment layout configuration. And finally, we also used a control mycopile, which was represented by the soil, which had been amended with a bulking agent. Okay. During the process, some parameters which were deemed to be critical were monitored on a daily basis. In particular, each mesocosm contained three moisture and temperature sensors located at 3/8 of the vertical profile, and data were required on a daily basis, and in particular every 30 minutes. And these data were useful to activate the heating or the irrigation system to correct these parameters within the set values. Unfortunately, we were forced during the experiment to make an amendment made by an diammonium phosphate solution, since despite a non-negligible concentration of total phosphorus, the assimilable phosphorus fraction was really low. And so what you see on the lower left side of the image is the time cuts of temperature, which in the early phases of the incubation were characterized by temperature peaks, but in some of the mesocosms, in particular in the higher type mesocosms, were characterized by the attainment and subsequent maintenance of critical values of temperatures ranging from 40 to 45 Celsius degrees. And this phase in higher type mesocosms was also characterized by a profuse colonization of the inoculating fungus. Okay, of course, sampling campaigns were done at 3 times, namely at the start of the experiment, after 3 months of incubation, and after 6 months of incubation. For this purpose, we built a soil corer made by a stainless steel cylinder with a cutting head and a sliding hammer to facilitate the insertion of the probe. And the cylindrical compartment could be opened longitudinally in order to extract the soil cores and to analyze this profile. What happened inside the reactors from a visual viewpoint? We observed a progressive compacting of the mass contained inside the reactors, which passed from a height of around 70-75 centimeters to around 45-55 centimeters. With regard to the visual presence of the inoculant, it was only detected in one of the 6 mesocosms analyzed, in particular in the CS2. And this, as we will see, has been confirmed by metagenomic analysis. Okay, so the upper plot and the table below refer to residual C12, C40 concentrations and to their percent depletion detected within selected time windows and the overall reduction. So the best mesocosm, the best performing mesocosm was CS1, where aliphatic hydrocarbons were depleted by 70%. The worst one was instead the CS3 mesocosm. Regardless of this, we observed a generalized reduction of the C18, C20 fraction in all the mesocosms. But an interesting thing is that the C24, C32 fraction hydrocarbons was removed at rates comparable to those of lighter hydrocarbons, C12, C18. Okay. Of course, we also performed a series of microbiological, biochemical, and molecular analysis of the methods of interest. As far as the enumeration of the cultivable fraction of microorganisms, we observed a significant increase in the densities of heterotrophic bacteria, followed by the attainment of a plateau. In the intermediate sampling, increases well above those observed for heterotrophs were observed for cultivar fungi. With regard instead to the fraction of hydrocarbonoplastic bacteria, we observed a completely different trend with respect to that of heterotrophs, characterized by a marked decline or insignificant changes in the intermediate time point, with the only exception of the CMP and CS1 mesocos, which have stood out for its alkane degrading capability. Okay, the indirect determination of bacterial and fungal abundances by real-time PCR of 16S and 18S ribosomal RNA genes, respectively, confirm a significant increase in both biota in 3-month-old mesocons compared to 0 time points, although the extent of increase for the fungal biota was markedly higher than that for bacteria, as we detected in microbial counts. In the subsequent sampling, no significant changes in the number of copies was detected as compared to the previous studies. In the mesocons of interest, we also performed the determination of 2 activities which are considered as proxy of overall microbial activity, in particular fluorescein diacetate hydrolase and dehydrogenase. And with regard to the former activity, it increased after 3 months of incubation in all the mesocons, while a further increase in activity at the treatment point was only detected in IF1 and again in CS1. A different pattern was observed for dehydrogenase activity, and this surprised us, characterized by a marked decrease of the activity as compared to the 0 time point, and followed by a partial activity rebound, which was observed in IF1, IF2, and again in CS1. And to determine the composition of microbial communities at the start and after 3 and 6 months of incubation, and to derive and to calculate alpha diversity expressed by the Shannon wave index, we perform a metagenomic analysis by Illumina metabarcoding of fungal, bacterial and fungal RNA genes. For reason of time, the data that I will show you refer only to the taxonomic level of the family, and to this data we applied a multivariate approach termed principal component analysis to highlight possible similarity, dissimilarity relationships, and to understand which taxon determine the possible separation of mesocons in the Latin space. We also performed okay, I go ahead. So, in general, overall, a generalized increase in bacterial diversity was observed in all the mesocons after 3 months of incubation, and the only mesocons that experienced a significant decrease in alpha diversity were CMP and IF1. In contrast to the prokaryotic community, alpha diversity of the fungal biota did not show a general upward trend compared to the 0 time point. The only exceptions were CS4 and to a lesser extent CMP. The stack bar plot in the left shows the relative abundances of bacterial families, and PCA biplot related to this data shows a clear segregation of zero time points from the remaining mesocosm. Along the second component, the variables leading to the separation of IF-type mesocosms from CS-type mesocosms, which clustered with CMP samples, were Brevibacilliaceae, the families Brevibacilliaceae, Peribacilliaceae, Chitinofagaceae, and Microcilliaceae. So, the hydrocarbon, to gain an estimate of the hydrocarbonoclastic potential of the bacterial communities, we also performed a functional metagenomic prediction using the PCRAS2 platform and focusing mainly on aliphatic degrading taxa carrying enzymes encoding genes which catalyze the first steps in the degradation pathways. And in particular, we took into consideration long-chain alkyl dioxygenase, alkane-1 monoxygenase, and alkyl succinase synthase, which is operational in anaerobes. According to this platform, to this analysis, the amplicon sequence variants present in our samples contain only genes encoding alkane-1 monoxygenase and alkyl succinase synthase. And in the zero time point, Moraxillacea, where the light blue stack, where the hydrocarbonoclastic taxon that contributed dominantly to the presence of these genes. In the subsequent sampling, a change in the composition of bacterial families contributing to the presence of these genes changed, and a relevant role was associated with other families such as the Micromonosphoraceae, Pseudomonadaceae, and Xanthomonadaceae. This slide refers to the taxonomic analysis performed at the family level on fungi. We see that in zero time terms point, we saw a very simplified situation dominated by two families, in particular Pleosporaceae, with several species belonging to the Alternaria genus, and to Bulderibacilliaceae, dominated by species belonging to Vishniacozyma genus. And the PCA biplot referred to this data shows that CS-type mesocosms and CMP mesocosms clustered in the right quadrants, while separation of zero time point with respect to IF-type mesocosms was due to the taxa Pleosporaceae, Trichocomaceae, and Chetomiaceae. With regard to this aspect, we detected several thermotolerant or thermophilic species in IF-type mesocosms. I remember that this mesocosm experienced an undeliberate rise in temperature, which led to an undeliberate microbial selection and to the inactivation of the inoculated species. So, although several studies, I go to the conclusions, and I apologize if I've been long. Although several studies conducted at scales much smaller than that reported here indicate the ability of this species of Pleurosmus striatus to actively compete with the indigenous microbiota for different reasons. In our experiments, inoculants based on this species have had a very low persistence, with the only exception of the CS2 mesocosms, where we detected the significant presence of ITS amplicons, both in 3 and 6 month old mesocosms. Operational considerations associated with indications based on the persistence of inoculum and, of course, degraded performance suggested among the possible configuration layouts treatment bed, the central monolayer, or at least a layer with a given thickness, might be preferred to the multi-layered one. The differential abundance analysis and the functional metagenomic prediction derived from the metagenomic analysis seems to suggest that improved alkanoblastic performance might be ascribed to a greater presence of amplitude sequence variants affiliated to the Saccharosspiraceae family, which contributed significantly to the personal genes coding from alkane monoxygenase, and other descriptors that we performed witnessed in favor of the superiority of these methods with respect to the other ones. Despite the absence of amplitude sequence variants associated with long-chain alkane dioxygenase genes, the C24 C32 was removed with rates comparable to those of lighter hydrocarbons. So I thank you for the attention. And okay, that's it.
Bueno, pues la última de las charlas correrá a cargo de Jorge Diamantino de Kepler y de Rafael Antón de la UAM, y nos van a hablar sobre lo que estamos haciendo en España, en el sitio español.
Vale. Bueno, pues muchas gracias. Para comenzar, dado que vamos mal de tiempo, voy a dar los datos clave que nos han llevado a luego el diseño final de la pila. Entonces, ahí. Para comenzar explicando, pues nosotros somos de la Universidad Autónoma de Madrid, yo del Departamento de Química Agrícola y Bromatología y Carlos del Departamento de Geología y Geoquímica, pero ambos del Grupo de Innovación Agroambiental Sostenible, punto clave, porque la mycoremediación es una innovación en el campo. Bien, ¿de dónde hemos sacado el suelo? El suelo proviene del Parque Energético de La Rábida, de Palo de la Frontera, en Huelva, y es un suelo real. Es un suelo en el cual se hizo una homogenización y se construyó una pila de unos 110 metros cúbicos, de los cuales 10 metros cúbicos se transportaron a la Universidad Autónoma de Madrid para hacer los primeros ensayos. Primer punto, caracterizar el suelo. Tras una caracterización, vimos que se trataba de un suelo muy arenoso. Este parámetro luego va a ser muy importante de cara a la bioremediación y mycoremediación. Segundo, que tenía una concentración de 10.000 miligramos por kilo de hidrocarburos totales de pH, es decir, estaba contaminado. Y tercero, que esta contaminación era reciente, que esto también influirá, como más adelante mostraré. Y como ya nos han explicado tanto los socios franceses como los socios italianos, tiene sus aproximaciones. Ahora viene la aproximación española. ¿Qué hongo hemos utilizado? Como ya ha explicado Carlos en la charla anterior, el sustrato postcultivo. ¿Qué es? Pues es el residuo que queda tras el cultivo a nivel industrial del champiñón, los sustratos que es la seta de ostra y luego eringi y lentínola. Aquí muestro una imagen de dónde sacamos estos sustratos, que es del Centro Tecnológico de Investigación de La Rioja, y en la imagen se puede observar cómo es un residuo, que hemos demostrado que ya no se debería de llamar residuo, sino se debería de llamar subproducto, dado a sus capacidades tan interesantes que tiene. Primer ensayo que hicimos, a escala de laboratorio. Vamos a ver cómo se comportan estos sustratos frente a este suelo real de CEPSA. Primer resultado. Hemos conseguido un 50% de degradación en 40 días. Y no solo eso, sino que el hongo era capaz de crecer en el suelo. ¿Vale? Aquí muestro cómo en todos nuestros análisis siempre hacemos los hidrocarburos totales y luego los hidrocarburos separados por cadenas. ¿Por qué esto es importante? Porque así vemos si una cadena más larga disminuye y aumenta una más lábil, significa que los hongos se están transformando. Si se degradan todas por igual, significa que la degradación es completa y se están convirtiendo en CO2. Este parámetro es muy interesante para intentar trazar la degradación que está teniendo lugar de estos contaminantes. habiendo visto que el primer ensayo salía bien, procedimos con un segundo a escala de laboratorio en el cual se adicionó aireación forzada para ver los diferentes resultados y se llevó a 60 días. Como aquí muestra la imagen, veíamos como el hongo seguía colonizando el suelo. ¿Resultados obtenidos de degradación? Pues en torno a un 60%, 70%. Para sobre todo el Agaricus bisporus. ¿Por qué este sustrato? Porque a partir de ahora, de los 4 que hemos probado, vamos a trabajar con el de Agaricus bisporus, a partir de ahora el champiñón común. Porque el champiñón, tras adicionarlo al suelo, hacía que aumentasen las poblaciones de, por ejemplo, alcalinogonadacea y spingogonadacea, que son degradadores de hidrocarburos. Ahí ya tenemos una prueba fehaciente de que se está dando una bioestimulación. Yo añado un sustrato en un hongo y me aumentan unas bacterias que me degradan hidrocarburos. Y ahora pasamos al mesocosmos. Todo esto está muy bien en escala de laboratorio, pero ahora vamos a los diferentes mesocosmos y yo voy a hablar del mesocosmos, por supuesto, español. El primer punto, diseñamos un invernadero y construimos un invernadero propio para hacer este ensayo en un entorno cerrado. ¿Por qué? Porque nuestra intención es los datos que saquemos utilizarlos. La principal limitación de modelizar es la calidad del dato. Y cuando yo hablo de calidad del dato es que tiene que ser dato robusto, reproducible, representativo. Entonces, por eso diseñamos esto muy controlado para que al menos todos los datos tuviesen el mismo sesgo. En los cuales se muestrearon siempre, como ya mostraré a continuación, diferentes parámetros del suelo. Y siempre aireación forzada con filtros para evitar la salida a atmósfera de los compuestos volátiles. Aquí estuvimos, bueno, está la he puesto para que se vea que son 10 metros cúbicos de suelo los que recibimos desde aquí, desde CEPSA. ¿Y cómo homogeneizamos? Lo primero lo hicimos manualmente, fue una tarea bastante ardua, pero hicimos que fuese un 10%, que era el ratio que aplicamos. Con este 10% llenamos nuestros microreactores. Como se pueden observar aquí 15, en nuestro invernadero donde está temperatura y humedad controladas. Podemos ajustarlo bien. Los diferentes tratamientos. Aquí simplemente quiero que se queden con la S, que es suelo. Suelo siempre tiene que haber un control en el cual no se adiciona nada para ver la evolución y la degradación natural. Y luego nuestros diferentes tratamientos con nuestro sustrato reproductivo, incluyendo este que lo llamamos de contingencia, en el cual se van a añadir surfactantes, en el caso de que en el resto no hubiese habido degradación. Primero, bueno, esto es la adición de surfactante, como la añadimos manualmente en nuestros mesocosmos de ese tratamiento. Y esto, bueno, aquí se puede ver una evolución al principio y tras 6 meses. Como se puede ver, el sustrato postcultivo ya ha sido integrado en el suelo. No sé, como se puede ver aquí esta capa superficial y aquí ya ha desaparecido. Siempre se monitorearon parámetros de humedad, muy importante, al final es muy dependiente de la humedad, conductividad, temperatura y oxigenación. Esto para cada reactor, para introducir, para tenerlo para el máximo control de cada tratamiento. El muestreo, este es un dato importante, siempre muestreamos de la misma manera que era de cada reactor, haciendo 9 puntos de muestreo, uniendo eso, y eso ya era una muestra compuesta de un reactor. Por triplicado, porque hicimos triplicado, ahí ya teníamos todas nuestras repeticiones. Dato, aquí solo he puesto los datos a los 90 días. Tenemos una degradación, aquí hemos conseguido un 60% de degradación. Y en este pongo la evolución de los hidrocarburos totales a lo largo del tiempo. En inicial, 30 días, 60 días, 90 días. Y de aquí 2 puntos importantes. Este sustrato, por ejemplo, el tratamiento SS verde, en 30 días disminuyó un 50%. Este es un dato muy interesante. Otro dato también interesante es por qué a los 180 todos se quedan con la misma concentración, incluyendo el control SOR, sin nada. Esto, nuestra hipótesis, lo hemos asociado a la biodisponibilidad. puedes degradar un hidrocarburo lo suficiente hasta que deja de estar disponible. Entonces ahí se para el proceso. Nuestro plan de contingencia, surfactantes, que esto luego se va a aplicar en la fila grande. Aquí, esta imagen la pongo porque es interesante cómo los perfiles de bacterias obtenidos para nuestro ensayo en pequeño y nuestro ensayo en grande se parecen mucho los perfiles. Esto significa que las poblaciones bacterianas se parecen independientemente de la escala. Y esto es importante. ¿Por qué? Porque aquí ya es un factor donde la escalabilidad no está afectando. Luego ya por último, esto es lo de las microtrash, un guiño a la presentación de ANCO. ¿Por qué? Porque nuestros datos de metagenómica sirven para avalar y complementar los datos obtenidos con la microtrash como nueva tecnología para poder evaluar a corto plazo, para poder evaluar la evolución microbiológica, porque al final el objetivo nuestro de Mesocosmos es intentar desarrollar un modelo para poder predecir cómo se va a degradar un hidrocarburo en base a la microbiota que hay en el suelo, porque al final es la bioestimulas y ella degrada. Entonces, ver potencialidad, al final se busca ver la potencialidad. Y por último, una foto corporativista de todo el equipo LIFE MySOIL. Y
vale, yo ahora voy a presentar la parte de Kepler. Kepler en este proyecto de investigación, al final, su principal trabajo es aplicar su conocimiento y experiencia en la construcción de biopilas. Y lo que hemos hecho, como momento referido, fue construir dos biopilas en la parte sur, que es lo que vamos a visitar esta tarde, en el parque energético La Rábida de Seville. Hemos construido dos biopilas, una de control y otra que le llamamos mycopila, que es donde aplicamos los tratamientos con los hongos. Con base a los resultados que ha presentado Rafael, del Mesocosmos principalmente, hemos diseñado la estrategia para recuperar este suelo, ¿no? Para eliminar los TPHs. Y consistirá en dos fases. Ahora mismo estamos en la primera fase, ¿no? en que las biopilas son dinámicas, y en la segunda fase vamos a pasar a biopilas estáticas. Y ahora lo explico un poco. El concepto, la diferencia de las dos biopilas es que las dinámicas lo que hacemos es la oxigenación del suelo se hace a través de volteo, con una retroexcavadora. Volteamos el suelo, nosotros normalmente hacemos una vez al mes este volteo, ¿vale? Mientras que en las biopilas estáticas, una vez que construyes las biopilas, se pone un sistema de aireación forzada. Y el suelo ya no se mueve. Es importante, ya hemos visto en otras charlas, que para los hongos, para no destruir las hifas que se van utilizando, lo mejor es las biopilas estáticas. Entonces, ¿y por qué estas dos fases? Porque la fase dinámica, lo que hemos hecho fue no añadir al hongo de momento, ¿vale? Lo que hemos hecho fue empezar por una bioestimulación, que hemos visto en el Mesocosmos, que era muy importante, la adición. Hemos adicionado el sustrato de Agaricus bisporus, que es el champiñón, pero sin inocular, o sea, los nutrientes con que empiezan antes de la producción de la seta. Esto es lo que hemos hecho y es lo que vamos a ver esta tarde. Y hemos añadido agua y la aireación va a ser por volteo del suelo. Luego, después de 2 meses, lo que vamos a hacer es pasar a estas biopilas estáticas, y aquí sí vamos a añadir los hongos, los sustratos post-cultivo que Rafa ha presentado, y vamos a añadir tanto de Agaricus bisporus del champiñón como también una capa en el medio de Pleurotus austriatus. También vamos a adicionar surfactantes para hacer que los contaminantes estén más biodisponibles, y conectaremos esto a una planta que estamos preparando. Aquí. Vale, entonces hemos construido estas biopilas al inicio de este mes, por eso aún no tenemos resultados disponibles, analíticos. Lo que hemos hecho fue extender la lona para impermeabilizar el suelo, y hemos hecho un traslado de la zona de acopio
que Cepsa tiene las tierras contaminadas hasta el local que vamos a visitar esta tarde. Hemos transportado 5 camiones, que en total son unos 100 metros cúbicos de suelo, y que hemos dividido en las 2 biopilas. Cada biopila tiene 50 metros cúbicos. Hemos mezclado el suelo, lo hemos dividido en 2 biopilas, la control y la micopila. Y la micopila es donde hemos añadido este substrato no inoculado del champiñón, que se puede ver aquí su apariencia. Lo que hemos hecho en la biopila control fue el volteo y añadir agua, y en la micopila hemos adicionado los sustratos y hemos adicionado agua. Luego esta tarde tendremos más tiempo para explicar con más detalles. Al final tuvimos la micropila control, micopila efecto antes de tapar, y después la hemos tapado con lonas y usando sacos de arena como peso. Ya se ha hablado aquí de la importancia del muestreo. Entonces lo que hacemos es dividir cada biopila en la mitad. De cada mitad hacemos 5 puntos de muestreo que lo mezclamos en una bandeja para tener una muestra representativa. Y además tenemos 2 muestras por cada biopila, A y B. De esta forma es nuestra forma de lidiar con la heterogeneidad que ya sabe que Laura y Jean-Michel hablaron en su presentación, que presenta el suelo a escala real. Y luego hemos mandado a analizar una serie de contaminantes que hemos hecho. Hacemos la separación de cadenas de C5 a C40 y también aromáticos y alifáticos. Luego también BTX, benceno, tolueno, etilbenceno y choleno, y los aromáticos policíclicos. También es muy importante monitorizar los nutrientes, porque es un proyecto biológico. Y luego, como hemos comentado al inicio, Kepler tiene su propio laboratorio biotecnológico donde hacemos el seguimiento de la actividad microbiológica. Hacemos por recuento en placa, vemos las poblaciones degradadoras de TPH. También seguimos la actividad enzimática como la hidrogenasa, y luego, por fin, la tecnología de biología molecular, la PCR, también hacemos el seguimiento del proceso. Entonces, ahora, creo que ya se comentó, pero se está preparando una guía genérica de la mycoremediation en este proyecto que se va a publicar. Y luego también Kepler tendrá una parte importante en la reproducibilidad de la técnica y transferibilidad a otros contaminantes. En este caso, en este proyecto vamos a probar usar la mycoremediation con suelos contaminados con HTF en las termosolares, y también vamos a probar este tratamiento. Entonces ahora nuestro reto es conseguir una eficiencia alta de eliminación de los TPH a escala real, adaptar esta tecnología a varios tipos de suelos y climas, y por último con la generación de la guía, un poco diseminar esta tecnología por toda Europa. Y aquí termino la presentación.
Bueno, a efectos de un poco de organizarnos, que vamos un poquitín retrasados en tiempo, vamos a abrir ahora una ronda de preguntas. Pediría a los ponentes que pudieran venir aquí a acercarse aquí, por favor.
Que dan all the chairs.
Y lo que vamos a hacer es, vamos a recoger, tendríamos Bueno, muy sencillo, ¿no? Es decir, si tenéis preguntas, por favor, pues hacerlas llegar y si son a mí, que no sea muy difícil.
Y si necesitamos también traducción, podemos hacer. Y también desde a nivel virtual, tenemos un compañero siguiendo también.
Sí, luego al final podemos, a veces tener algún tiempo, responder alguna pregunta que se haga por el chat. Sí,
Para romper el hielo. Quería preguntar, desde el ámbito de las termosolares y del HTF, si no he entendido mal, todos estos proyectos ahora en Huelva vais a traer sobre hidrocarburos, pero sobre el HTF del día después, no he entendido mal.
sí, haremos ahora las biofilas con HTF. Lo que pasa, hemos visto, adelanto, que no les gusta a los hongos del HTF.
No se comporta igual que
No les gusta nada. Entonces, la estrategia con este contaminante va a ser diferente. No podemos aplicar al hongo directamente. Lo que estamos pensando es hacer un estrato enzimático, las enzimas fúngicas y aplicar el estrato enzimático. Porque al final el HTF realmente es un antifúngico. Entonces,
los proteínas lo convierte en un tipo de cálculo para que sí tenga efecto.
en este caso, HTF sí que tenemos bastante experiencia, que nuestro consorcio microbiano funciona bastante bien. La idea con la mycoremediation es ver si podemos ir un paso más allá, hacer con que el tratamiento sea más efectivo y más rápido.
Claro, es que, por ejemplo, un punto que hay que entender, cuando mycoremedias algo, es el hongo el que son enzimas que echan medio ambiente y esas de la... Entonces, el hongo te tiene que crecer, porque si no crece no va a echar enzimas. Entonces, el HTF justo, por escala de laboratorio, no crece. Entonces, lo que vamos a hacer es forzar echando directamente las enzimas, cultivándolo, porque ese es el extracto enzimático. Y esa es la aproximación que se va, porque el HTF hemos visto que al final es una bioremediación, porque lo que se va a hacer es su consorcio, estimularlo y ver hasta qué punto podemos acelerar, porque al final consiste en acelerar al máximo el tiempo, minimizar tiempo de maximizar degradación.
Al final de aquí tendréis unos datos a qué degradación se llega, luego de alguna manera lo transferís o bueno, aquí llega o generadas.
Sí, los datos de principio están hay una página web del proyecto LIFE MySOIL y normalmente ahí bueno, está colgadas todas las presentaciones. La página y también el canal LinkedIn del proyecto. Bueno, también hemos hecho ya un workshop, se está planificando un workshop final del proyecto, donde se divulgarán todos los resultados.
En el caso que aplica, ¿no? Para HTF en este proyecto estamos colaborando precisamente con una planta termosolar, que es la planta termosolar de Lebrija, a través de Northern Power, que es digamos, la propiedad, ¿no? de esta planta y que nos ha permitido pues, realizarse.
I have a question for Alessandro. Do you have any hypothesis on why the dehydrogenase activity decreased between time 0 and time 3?
So, as I mentioned, we were rather surprised because we have managed several contaminated sites characterized by aliphatic or aromatic contamination. Generally, the trend is an increase. So, as far as the depollution, decontamination proceeds, you have an increased activity of dehydrogenase. During this LIFE MySOIL project, whichever the metrics we have taken into consideration, we have always observe a decrease from the zero time point. And we have not found any valuable explanation that might justify this kind of pattern, even in the literature. So we are searching for one. So generally, the dehydrogenase activity expresses the pool of reduced nucleotide coenzymes. This is dehydrogenase activity. We can say that under the condition that we have tested, we have a reduced pool of these nucleotides. But we do not know why.
Thank you.
Entonces, en la última presentación, Rafael, mostraste el desempeño de remediación del mesocosmo, de la control y las demás. Y el resultado era prácticamente el mismo.
Claro, a los 180 días sí, al final la degradación, lo cual significa que eso es lo que yo comentaba, que a los 180 días se llega a lo mismo. ¿Vale? Eso aparentemente es un mal resultado, ¿vale? Al final llegas a lo mismo. Pero porque eso mismo, lo que queda, no está disponible. Entonces, por eso lo de surfactante para biodisponibilizarlo. El resultado bueno es que a los 30-60 días se llega a eso muy rápidamente. Entonces, la bioremediación ahí es clara. Claro, solo que si lo dejas y no lo... Por eso también la importancia de los datos y de ver, porque si tú lo dejas, vas a llegar a eso, pero va a haber un máximo. Y ese máximo no se va a poder superar a menos que lo trabajes de alguna manera. Y eso es uno de los resultados que estamos viendo, que hemos visto en el proyecto, y por eso de cara al diseño de la pila grande, que al final este es un proyecto demostrativo, eso es muy importante. En este proyecto, la parte de laboratorio es imprescindible para estudiar un poco qué pasa con el suelo, pero lo que se valora y evalúa es la pila grande, al final lo que demuestra la tecnología, si vale o no. Entonces, por eso... Y luego otro detalle que también es muy interesante es lo de las texturas, que yo no me ha dado tiempo a aumentar, llevo mal de tiempo, que el suelo sea arenoso es un problema, porque todo el agua que eche se va rápido. Entonces tienes que estar continuamente regando. Y claro, en un suelo arcilloso como tenían, que ahora les preguntaré about your texture. Yo soy texture. En su suelo, por ejemplo, que era arcilloso, pero arcilloso a un punto de que puedes moldear con ella jarrones. O sea, claro, en ese suelo, ahí la aireación cómo va. Es un problema. Entonces en las guidelines estamos cubriendo esto. Como un análisis del suelo es imperativo inicial para poder tener una... Y bueno, por eso las guidelines se van a basar en eso.
Yo hago un inciso muy pequeño y le daré la palabra a Alessandro, que si hace falta me traduzco. La biodisponibilidad, que es un concepto muy importante. Puede que uno de los principales factores por los cuales la microremediación o bioremediación en general no funciona. Tenemos que saberla caracterizar, qué biodisponibilidad tenemos al principio y cómo podemos hacer más disponible este contaminante. Aquí habrá, porque por muy rápido que hagamos la bioremediación al final, si el nivel donde llegará es hasta ahí, no es válida la tecnología, a no ser que lo podemos bajar hasta aquí. ¿Quieres que te traduzca lo que te ha preguntado o...? No, that was talking about the texture.
Yeah, I was involved with the other partners about the problems that you have experienced about the soil texture, which is a main parameter that should be taken into account.
I would like to regarding this aspect, because the bioavailability is extremely important, especially as far as hydrocarbons are aliphatic hydrocarbons are concerned, because they have very extremely low solubility in water. So pollutant mobilization from the solid phases to the water phases might be negligible in some cases. So it is true that some bacteria develop biofilms over colloidal surfaces, but this might not be enough. The problem is to obtain a recognition of the methods which are currently involved in the determination of bioavailability. There are several options. The formal options were based on multi-distractants. such as, for example, propanol or propanol-methanol mixtures. And then other methods have been established, for example, based on the use of strong sorbents, such as TNAX, or compounds able to form inclusion complexes. For example, UAM have used this approach to determine bioavailability of polycyclic aromatic hydrocarbons. In the last years, we have seen that some papers have highlighted the attention on several soils to see whether biotreatability and bioavailability assessment might be correlated. And there are an increasing number of papers that are doing this. And I think that this is extremely important, especially as far as aliphatic hydrocarbons are concerned. So bioavailability issue is really an important issue. We have not faced it during this project, and this is, we apologize for this, but I think that this is an issue that has to be taken into account.
Also, I want to add that it's really, Amy, what you said, the methodology, but when you are using a methodology, how to make sure that that methodology is not affecting the soil itself. So testing the viability, it's really difficult also.
I don't think there is a problem which is texture driven. I mean, you use a concept, you use different concepts to determine which fraction is a labile fraction. In the sense that the contaminant is not tightly bound to the colloidal surfaces of the soil. So there are several approaches. One and other emerging approaches is the use of supercritical fluids. For example, there is a sequential supercritical fluid extraction with carbon dioxide that have been successfully used and is recognized at least for polycyclic aromatic hydrocarbons, and that gives reliable estimates of bioavailability. So you can know that if you determine a given contamination level, you can also determine which fraction of this contaminant pool is labile bound. And so this is susceptible to be biodegraded, at least as higher chances that the other fractions to be degraded. It can be mobilized easier.
And regarding availability, we may also check that chemoavailability means availability for chemical reaction is almost the same pattern. The same is overlapped very well, because if it's condensed in a drop, it's very hard to oxidize or to reduce, as it was presented this morning for other type of components. So availability in general, bio or chemo, is almost the same population of pollutants in the soil. And regarding soil structure, if we consider it as an agronomical point of view, very good soil you may find in a vegetable gardens or in a forest. This a soil, and we know we have a lot of proof yet, recent work on this, that you need to have old carbon, new carbon, very fresh organism, insect, long-duration saccharinians, and all of this we don't have in an old industrial soil that was no life. It is in gasoline station or in a refinery. We don't have this. It's always a bad structural soil. When you mix it with water, it make a mud. The aggregates are not strong, and it's very hard that in 6 months we recover the structure. And even if we had some fresh organic matter, most of the time we don't observe the time enough to check this gain in structure. That is one key point to have the gain in biological activity and activity against the pollutant.
The problems of biological approaches to the elucidation of the bioavailability are two. The first one is that they are extremely time-consuming, and the second is that the biological indicator, as you mentioned, is widely variable. So you do not obtain a straightforward indication. Is that compound labile bound to the soil fractions or not? So I prefer chemical approaches.
Yes, we have some tools to approach it.
Yo diría que cerramos, yo tengo un último pregunta, pero cerramos ya que somos un pequeño grupo, tenemos 1 hora para tomar el cóctel y intentamos, podemos seguir discutiendo, pero tenemos que cumplir el horario al salir a las 5, porque así lo tienen programado nuestros amigos de Seville. Yo, como última pregunta, me permitís, los tratamientos microbiológicos al final son todavía mucho más antiguos, tan antiguos que la Tierra, la biología de la Tierra. Es decir, es algo que hace la naturaleza siempre. No sé si habéis estudiado un día libros de agricultura. Allí todos los procesos de degradación microbiológica hace la naturaleza al degradar lignina, está muy investigado. Se puede aportar mucho de la agricultura. Es dentro de las técnicas de descontaminación es la que está copiada a la naturaleza. Es lo que hace la naturaleza, por eso se puede decir es la más sostenible. Lo único que hacemos es un poco acelerar, y los hombres siempre tenemos prisa. Bueno, aceleramos un poco. Pero mi pregunta es, yo supongo que los académicos y vosotros habéis oído hablar de la biomimesis.
Biomimesis.
Biomimesis, ¿no? Es un ramo de ciencia que realmente no se puede decir, pero es una rama de ciencia muy importante que hacen empresas como Boeing para bajar el ruido dentro de sus aviones.
You mean protocol feeds, synthetic protocol feeds, for example.
No, it's a biomimicry.
Huh?
How you can leverage natural processes, natural
design. Biomimesis, lo que quiere decir aprender de la naturaleza, como se hace estudiar. Hay laboratorios que se pueden alquilar en la selva de Indonesia o Sonia. Puede ser alquilar un laboratorio completamente equipado, vives allí en plena selva y copias. Entonces, nosotros en tecnología microbiológica no hacemos esto, pero de forma, me parece, inconsciente. La pregunta es por qué nadie hace este enfoque directamente desde la biomimesis. Por eso tu proyecto LIFE.
Further examples of biomimicry.
I got an answer to that because that was our starting. So we started. We were doing biomimicry biomimicry was now 13 years ago. We're starting that. We're trying to advocate. Then we started the company trying to implement this, and that's the starting point of why we're here today and why we're developing the tools that we're developing. That's a collaboration that we have now with L'Oréal, working on how to leverage that with different companies into the key elements within understanding how nature works in a way to open up issues. To go towards your understanding or perception about taking the lab, putting into the forest, understanding and studying what's happening there. I say that the answer that we're building is when I call into the modelization platform, is to identify understanding how an organism works from the genetic point of view, being able to modelize that, and that's technologies that are now mature. To be able to drastically add 2 elements there. So the first one is selecting from nature, understanding from reading genomes, which are the organisms that do have that capacity. That's one element. But also, the other side, being able to simulate that to understand before having to experiment. Because there's a problem of volume of information. we have to be able to sort out, say, okay, like we did, so we did in the first phase, so we tested 71 strains. How did we test them? We took them, we exposed them to a contamination road to see, okay, which were the ones to be capable of throwing with just converting the contaminant to carbon source. That was the selection point. Then we expose them to soil samples, then we expose them to. It's a very long and tedious process. And what we're currently doing, and you see that, is that in 2 months' time, through a simulation, we can already anticipate that we're coming up now with new strains that have been the candidate that we had in the beginning. And then define, and also a combination. Okay, then we have a combination of this organism with this organism, this one, because gathering will make sense. Nothing is the next step. How we can leverage the evolution of nature, transforming that into actionable points. Because the key problem is if you have to transform the problem into a function. So what are in nature the function that do correspond to my challenge in terms of industrial, in terms of, this is a complex one. And then comes understanding this part and then transforming it into actionable points. That's also very energy intensive. It takes a very long time to develop biosphere innovation because it's a long process, it's true for the efficiency. And I think now with involved and also your use of the metagenomic data and the elements in the consortium, you see that technologies evolve fast ways where you can use new technologies to really go faster.
Yeah, but I do not change my mind. So I think that biomimicry still remains a very appealing perspective, not the factual reality. So if I can imagine some biomimicry system, so I can think about synthetic protoporphyrins, some rubidium complexes which simulate polyphenol oxidase activities, or manganese dioxides preparation. But I don't see so many examples of a system with a robust and verified capacity of bringing about some work. So this is my opinion, but probably I'm ignorant on the topic.
Ya vamos a un caso muy práctico de biodegradación, tomamos el...
Yo creo que tenemos que despedir a la audiencia que salga online. Vale, pues muchas gracias. Creo que ahora son unos 20 y pico personas que nos han seguido. Muchas gracias por vuestra asistencia. Si tenéis cualquier mensaje, comentario, lo podéis mandar al chat y os responderemos lo antes posible. Y pues estamos aquí, como ha dicho Norbert, vamos para...
Yeah, I'm curious because I don't know.
At some point there were 29 people. That's
Gracias.
Muchas gracias por vuestra asistencia, por la presentación y continuamos, ¿no?
Sí.
Gracias.